for coming to this defense. I'm going to present the work of almost 5 years that I've been working on these things. Thank you, Oriel, Amnon, jury, the committee, for being here and for guiding me through this process. So today I'm going to present the essays or the results of the essays that we wrote on groundwater pumping subsidies and the behavioral changes of users. The way I structured this presentation is I'm going to give you like a brief summary of what's going on between subsidies and groundwater exploitation. Then I'm going to give you the context of the groundwater in Mexico and what's going on there. I'm going to introduce what is called Tarifa 09, which is the subsidy to electricity that we have in Mexico. And then I'm going to introduce the first model that we use in the first paper. And then after that, we're going to introduce the experiments that we conducted in the lab and in the field. So I decided to not break it down by essay. I just wanted to have it like flow as one continuous presentation, but the three works are included in here. Okay, so let's talk about a little bit of subsidies and overexploitation of aquifers. So in the world, we have some examples of countries that are have pumping subsidies, which include China, India, Pakistan, USA, Spain, and Mexico. This is only a couple of examples. So all these countries have subsidies for pumping groundwater. Now, if we look at which countries have overdrafted aquifers, it's no surprise that most of the countries that I mentioned are in this map. Today, I'm just gonna focus on the case of Mexico, but just keep in mind that this is a broader problem. It's not only pertaining to Mexico. Okay, so what is going on with the groundwater in Mexico? First, I'm going to give you the perspective of economic activity and water availability. So this part here in yellow concentrates 80% of the population, and it also concentrates 80% of the economic activity. The part in blue concentrates the rest of the population. However, you can see that only roughly 30% of the water resources available in the country are just in the yellow part. This is due to this distribution of precipitation. This map is changing rapidly because of climate change. So these yellow areas are expanding. So now we're gonna have a more drier country. But this is just a historical average of precipitation between 81 and 2010. So you see how the middle and northern part of the country is very dry, and it's the part that concentrates the most economic activity and the most population. So how does that take us to the overexploitation of groundwater? Well, you see that where it is dry, the red dots or the red parts of the map represent the overdrafted aquifers, the aquifers that are overexploited. So what does that mean? We can see a relationship between economic activity, population concentration, the precipitation patterns, and the overexploitation of aquifers. Now, what is this subsidy that we are talking about? In 2004, subsidy called Tarifa 9 was introduced as a stimulus price to electricity for irrigation. This was in response to the opening of the agriculture chapter in NAFTA that was signed in '94, and it came into play until 2004. So we didn't do our homework, and we had to have like an emergency measure to make our exports competitive. So what they come up with? This subsidy. It roughly subsidizes up to 80% of the electricity cost for pumping. It's 20 cents of peso per kilowatt hour during the night and 40 cents of peso per kilowatt hour during the day. Now it has around 105,000 users. Its concentration index is really high. It's 0.9. And what does it mean? It means that there's very few producers that receive a lot of money in subsidies. In fact, there's like 3 producers that receive more than $50,000 in subsidies. And there's 30,000 producers that receive less than $50 a year in subsidies. So it's very concentrated in very few people. That's why it's the Gini index is 0.9. And the last number that they have published is that in 2013 they spent roughly $900 million in this subsidy. Now, what are the effects or the negative effects of these subsidies that we have found? Well, first, it creates artificial rents. There's land and there's crops that will not be profitable if it wasn't for the subsidy. It doesn't give the right incentives for technology change because farmers don't have any incentive to change to a more efficient technology if they know the water is free or almost free. There's an horizon of a strategic behavior. What it means is, if I know my neighbor is going to pump at the same price as I'm pumping, then I'm going to want to pump more than him before the aquifer dries out. So it creates this competition for resources, and that's the strategic behavior. And well, there's a biased selection of crops because, as I mentioned, there's crops that are very intensive in irrigation and wouldn't be profitable if it wasn't for the existence of the subsidy.
I've got a question.
Yes.
I mean, the aquifers, are they of the same size or they differ considerably from one another?
They're very different. These maps map the size, the real size of the aquifers. All these are it's over 600 aquifers in Mexico. 101 of them are overdrafted. Some of them are very big, like this one in Baja Sur, this one here in Chihuahua. Some of them are very small, like these ones on the coast. So they vary in size, and of course, the effects are relative to the size of the aquifer. But in general, that's true. What I just mentioned. Okay, so we wanted to explore the responses of users to changes in the subsidy structure, and we went to the literature. We found some works on groundwater exploitation, groundwater economics. Gisler Sanchez, which is one of the most prominent articles in literature regarding this. Also, Feinerman and Knapp that talk about groundwater use and regulation. So we started exploring this literature, and we came up based on those models with a simple, well, not simple, but a model that predicts the behavior of groundwater users when the subsidies are changed. So we take the benefit function that is used in Feinerman and Knapp, where this is just the integral from 0 to Q of the demand of water, and Q represents the total water consumed. Now you see there are some other factors. So in this model, we decided to consider not only the use of groundwater, but we also considered the use of surface water, which in this case is exogenous. It's not determined by the model, but it still is in there. We also considered the infiltration factor, which is the surface water that goes into the aquifer, and the W, which is the groundwater consumed. We also have a cost function that includes the groundwater consumed in the present period, the water table depth, the maximum depth of the water table, the electricity required to lift 1 million cubic meters for 1 meter, and the subsidy level. We also have a fixed cost, which for simplification matters, we're just going to assume it's 0. Although we acknowledge there could exist significant fixed cost, but for simplification, we set it up as 0 in this case. Now we take this benefit and cost function and we establish our optimization problem, which again is just an intertemporal optimization problem in an infinite horizon where we see here our benefit function, our cost function, and we have here our equation of motion, which is going to determine the level of the water table depth in the next period. So that's with xt plus 1. And it includes the infiltration rate, the surface water allocations. This is multiplied because this rate times the water surface water allocations that go back to the aquifer contributes to this. Then we have the deep percolation, which is the infiltration of the water that goes back into the aquifer after irrigating the field. We have a recharge rate, and these two, which are geological parameters, the area of the aquifer and the storativity of the aquifer. We took this model and we simulated it for 200 periods, and these are some of the results we got. We did it with many sets of parameters just to check the sensitivity, but I'm just going to mention these results just for the sake of time. So, what do we have in here? This is the water extractions in millions of cubic meters, and you can see that the extractions under status quo, which is 80% of subsidy level or 20% of the cost, are way higher under status quo than under elimination or decoupling, which I'm going to mention in a little bit. Why is that? The water table depth under elimination, you can see that it stabilizes really quick, and it reaches only like about 500 meters, whereas the status quo, like, it goes very, very deep. This is measured with respect to the sea level, so that's why these numbers are like that. It could even go negative if the aquifer goes below sea level. We did it for 2 aquifers for Leon with real parameters of the aquifer, and we did it for Kern County just with the same parameters used by NAP and by Feinerman and NAP. And we see the same thing. Okay, so you might be thinking, what is going on in here? This sudden drop in here is because up to this level, up to these periods, the aquifer collapses. Like, suddenly it becomes very, very expensive to draw any more water from the aquifer, so it just collapses. We measure this area right here and this area right here to compare if the elimination was a yes.
Can you, before you continue, because you mentioned elimination and reduction, so maybe just define what is elimination.
Oh, yes.
Is it important?
Yes.
Before you continue.
Yeah, thank you. We tested 3 policies against the status quo. So the first one was elimination, which is probably the first policy that comes to mind when we set the problem, and well, the easiest thing to do is just get rid of the subsidy, right? So that was the first policy that we tested. The second policy we tested was reduction, which was taking the subsidy from 80% to 50%. And then the third policy was decoupling. In Mexico, the subsidy is given in a volumetric manner, which means farmers just pay a smaller price on electricity. So it's per volume of electricity consumed. So decoupling, what it does is it takes out the volumetric part of the subsidy, meaning we will charge farmers the whole price for electricity, but we will substitute it for a cash transfer. So we will calculate their consumption over a series of periods that we determined previously. We calculate the average subsidy they received in those periods, and then we give them a transfer every single period after. So we substitute the subsidy in a volumetric manner for just a cash transfer that is constant. It's just an average of the previous period. So those are the...
What is the rationale of doing it?
Okay, so it's the power of lobbying of the farmers associations in Mexico is they are overrepresented in Congress, and they are overrepresented in local governments. So politically, it's very difficult to remove a subsidy without having any political consequences. So one of the treatments that we came up with was decoupling to avoid or maybe reduce the political cost of changing the subsidy. So if we want to avoid a revolt, we want to make it as smooth as possible. So by giving them a transfer, it's almost like tricking them into thinking they are still receiving the subsidy, which they are, but it's in a different manner. Okay? So thank you for that clarification. Yeah. So we measured these two areas just to make sure that we were not overestimating the impact of eliminating the subsidy, and the whole the whole amount, the total amount extracted under the status quo is still higher than the total amount extracted under elimination. And this is what happens to the water table. You see, it goes very deep, very fast, and then once it collapses at the 50th period, it just stabilizes because it's not profitable to draw one more cubic feet of, or feet of water. So again, we measured the effect, and elimination and decoupling still has the same effect. So these are the differences between eliminating the subsidy and decoupling the subsidy. So you can see, and I'm not going to spend a lot of time in here, you can see that the difference is not even noticeable. What for the water table debt, for the annual net benefits is exactly the same result, basically. Now, what do we do with these results? So first we saw that elimination and decoupling were as effective, at least theoretically, in our computer simulation. There were consistent results with two different aquifers, one in California, one in Mexico, with two different sets of parameters. So that was encouraging. And we got some testable hypotheses that we wanted to take to the lab. And that's what I'm going to speak next. So after we got these results, we say, well, now what do we do with them? We want to take them to the lab, but we faced that the model in Federman and Knapp and Giselle Sanchez was too complicated to have people understand because it had deep percolation, it had infiltration rate, it had surface allocation. So it was too much for subjects to understand. So we used another model that does exactly the same thing, just measures things a little different. So what are the main variables that we're going to check in these models? This is an abstract representation of an aquifer. We have our pumping here. So we measured the height to the water table. We chose the height to the water table because it's easier for subjects to understand that the aquifer is going deeper with respect to the land level, with respect to where they are standing, instead of measuring it with respect to the sea level, because that kind of gets confusing. So that was the first change. We use the water consumption, like the requests of water that they're going to make, and the price and subsidy level. So these are the main variables that we're going to use in this model, although we have other variables just for control and optimization matter. So this is how our optimization problem looks like. It's very similar to the one I presented before, except our benefit function now looks a lot more simple. It does not have any quadratics. It's just a simple multiplication between just a factor that multiplies the level of water requested times something, so it gets a benefit from that. UT is our water extraction in time t. This is going to be our water table level, the height of the water table. The subsidy level, the price for electricity. As I mentioned, this is our benefit function. And this is our cost function. And as you see here now, as the aquifer becomes deeper, the cost function tends to infinity. So as this number tends to 0, this thing tends to infinity. So the extractions get more costly once the aquifer becomes more deeper. And this is the equation of motion, which is going to calculate the state of the aquifer for the next period. And it's just a very simple calculation. Is the amount of people in the aquifer times the requests minus the recharge rate. And these are our geological parameters, the area and the storativity. For our purposes, the aquifer, which is considered just like if it was a pool. So this number, the storativity, is going to be 1, just for people to understand it better. We know in the aquifer of them, the storativity is like 0.11, and it varies across the aquifer. But just for simplification purposes, here is just 1. Now, what are the predictions that we got from here? First, how does the height of the water table behave with respect to the subsidy levels? So you see, as the subsidy increases, the height of the water table does the same thing. Like it becomes deeper. Yeah. Remember, 0 is the level of the ground, and as we go deeper, that's the bottom of the aquifer is 250 meters. Okay. So as we see, as we increase the level of subsidies, the depth of the aquifer, the height of the water table is increasing. Now, we did the same thing, and we simulated this model for 100 periods to see what happened. And after a certain number of periods, the height of the water table just becomes almost, the trend becomes flat. It's just playing around those numbers. You know? It stabilizes, it reaches steady state. So we simulated again the same treatments. Status quo, which is the blue one, and as you see is the deepest one. Then reduction is the second deepest one. And then elimination and decoupling, that reaches the steady state at about like 140 meters. Again, in this model, we got the exact same results for elimination and decoupling. That pattern that we reach in the steady state of the water table is explained by the predicted extraction path. So you can see that the subjects will want to extract the maximum they can until it becomes not profitable, until they start losing money, where they go to 0. But because we have a recharge rate, for the next period it will become profitable, so it will go again to 10. And they will deplete the aquifer, and they go back to 0, and so on, that up to whatever number of periods we play. Now, how do we design the experiment? Well, for the laboratory experiments, we used the behavioral lab at the Anderson School of Management at UC Riverside. Thank you, Professor, for letting us use that. How do we do it? Well, we use their recruitment system, which is an online recruitment system. It sends a blast of email to a list of undergraduate students that are registered in that listserv, and they register for the experiment, and then we get it. We get the list, and then we invite them to come to the lab. What conditions did we test? Status quo, reduction of the subsidy, decoupling, and elimination, no subsidy. How did we do it? Well, we had a paper game. And the reason why we use paper and no computer is because we didn't know what were going to be the conditions in the field, and we wanted to have a similar design in the field and in the laboratory. So it was a 2-stage paper game. In the first stage, everyone played status quo. So 80% of the subsidy and the same parameters as everyone. They were giving tables. You remember that? Thank you for testing the game for us. They were given tables, like big tables, where they were told the depth of the aquifer for that period, and they could see from 0 to 10 how many units of water they wanted to withdraw from the aquifer. They will make the request. That will be associated to a profit level, and then we will calculate the water table for the next period, and so on and so forth. So that was the main task. And yes.
They do it in a group, and they get full feedback about the extraction levels of the other group members?
Yes, I'm going to go to the group part in a little bit. Yeah, so the experiment is set to have 6 people, groups of 6 people, and we decided first to have 6 groups of 6, but because of the size of the lab, we only could accommodate 5 groups of 6. So I'm going to go there, but yeah, and they were assigned as random. So there were no previous designation. They did communicate with each other. So, but I'm gonna go there. So that was the 2 stages. First status quo, and then the next they did the same thing, but they were told that the subsidy has changed. They were giving a different table, and they will play the same game again. Now for the field experiment, we went to the city of León, Guanajuato, in Mexico. This is the state of Guanajuato. This is the aquifer that is in the city of León. And we recruited farmers from the state of Guanajuato. We have the help from the Water District and the Irrigation Association, as well as the National University in Guanajuato. It was open to all farmers that willing to participate, but I put an asterisk there. Okay, first, we encountered some difficulties because the university wanted to invite their subjects, people that already work with them in some other projects, some different projects. They wanted to invite them. And then once we got the subjects to come to the campus, some of them didn't know how to read or how to write. So that was a difficulty. So we had to turn away some people because they didn't know how to read. Other than that, it was open to all farmers willing to participate, except with this caveat that they needed to know how to read. It was performed there at the campus in León. And why did we choose Guanajuato? Well, 70% of the water is used in agriculture. 71% of the water they use comes from the ground. And their extraction rate or extraction recharge is 1.3, meaning that they extract 0.3 more than what they get recharged in the aquifer a year. So they are overdrafting their aquifers. We play the same conditions, status quo, reduce subsidy, decoupling, and no subsidy. However, in order to make it easier, instead of having the tables and explaining everything, it's the same procedure, except we do it in a computer with Google Sheets. And I'm going to show you how it looks like.
I have a question.
Yes.
You seem to be treating the farmers as homogeneous.
Yes.
But you said before that some are rich and some are poor. So have you found in the analysis any difference? Have you done any analysis as a function of the richness or the wealth of the farmer? Or do you have any information about it?
Yeah, I was going to go there. When we applied for the IRB, we established that we were not going to collect any information on the farmers. So in the water agency, they gave us a letter also saying that they will keep the information of the farmers confidential. So we did not get to see any information of the farmers except when they signed the receipt. We got to see their name. But that was it. We did not collect any personal information. And this was because of IRB purposes. We didn't want to go the step beyond to collect data.
So the local IRB is here.
Yeah, the UCR IRB, yeah. The IRB is a human resource board that approves research with human subjects.
The general requirement.
Yeah. Okay, so, but yeah, in our model, and thank you for the clarification, all farmers are homogeneous and they have the same size of land, they have the same crops, and this is just for simplification purposes, just to make the experiment as simple as possible so subjects will understand and they will have no problem playing the game. Now, how did we design it? Okay, so this is groups of 6 subjects and 5 groups of 6. So we had 30 people per condition, except, as I mentioned, in the field that we had to turn away some people because of this reason that they didn't know how to read. Now, what are the results? I'm going to compare by treatment, both in the laboratory and the field, and I'm going to comment a little bit on that. So, laboratory experiments for elimination, we saw that in general, students were playing very conservative the first periods in elimination. Their total requests per group were very, very small. And once they realized that they are playing for money, they started playing more aggressive. So you can see how it shoots up to 46, and it sort of keeps a steady trend until the last period. Once we apply the treatment for the second part, they already know that they're playing for money, so this conservative moving here is not existent once we try to apply the treatment. But you can see that consistently the requests for water under the treatment are under the status quo, except this one where they were expecting the experiment to end, so they wanted to request more water. I forgot to mention the experiment. The end of the experiment was at random, so they will play a number of periods that was not determined previously, and it was determined by drawing a chip from a box, and it was 15% of probability of ending the experiment, well, the game. So we had, I don't know, it was like 17 chips. You gave me the box, and we had I think 5. It was 15% probability of ending the game. So we will draw a chip after each run. We will draw a chip, and if it was white, we'll keep going. If it was blue, then we'll stop. Now, how does these translate to the yes?
The units on the y-axis, the minimum is really 0 and the max is 60. Is that correct?
Yes.
So I noticed that in the upper left, the difference is really rather small. It's between 41 and 46 for the farmers. Not only it's considerably larger discrepancy.
Mm-hmm.
I don't remember whether it was mentioned in the paper or not. Maybe in the comparison.
Yeah, I didn't mention this in the paper yet because I still have to do some work in there. But yeah, we saw that students tend to play more steadily and more conservative than farmers at some point. And yeah, as you mentioned, the difference are larger, but also when we check the treatment effect, there's also a difference there between the field and the lab. So I'm going to speak about that a little bit later. So how does this translate to the height of the water table? So remember this difference right here? Well, it translates it accounts for this trend. So in the elimination treatment, the trend is negative, and it's a little bit deeper in elimination than status quo, but then the trend is broken here. And you can see how during status quo it goes like very deep, and this trend kind of breaks in here. It kind of reaches a steady state here. Now for the field, you can see that consistently the withdrawals from the aquifer, the total requests per group under status quo are higher than under elimination, and that is very, very clear when we saw the height of the water table here. Like, it has a negative trend, and then it just stabilizes over there, whereas the status quo was like very, very deep. Now reduction. So again, this is the exact same graphs. I'm just going to show you how on the reduction, it's under the status quo requests, although at the end, as I mentioned, there's this expectation of the experiment to end, so they start playing very, very aggressive. That explains this thing here. And in the status quo, they are consistently higher, except, as I mentioned, this part at the end. And that translates to a deeper water table in the status quo than in the reduction treatment. Now, remember I told you, or I showed you the graph of the peaks in the extraction path? So we observed something similar with the farmers. They will go very high, then they will go very low, then will go very high, then they will go very low. They, even though it is lower, it's not very noticeable. And when we conducted a statistical test on the mean difference in this between status quo and reduction, we realized that it's not statistically significant. So even though it's lower, it's not statistically significant. So we can't account for a reduction in withdrawals under this treatment. However, in the height of the water table, we can see a difference. Under status quo, it goes deeper than under the reduction treatment. But as I mentioned, this is very blurry. It's not statistically significant, so we can't assert that the mean of status quo versus the mean of reduction is smaller. Now for decoupling, for decoupling, we have that it has the most dramatic effect amongst all treatments, at least in the laboratory and also in the field. So you can see that the difference are like dramatically more in the total requests in the laboratory and translated to the height of the water table. So what do we do here? Again, I'm gonna explain. After the first part of the experiment, we calculated the subject's average consumption and average costs, and we gave them the subsidy as a transfer each period. So they were told, each period you're gonna receive X amount of tokens, and that translates to your profit. So whatever profit you see in your table, we're gonna add these amounts of tokens. And this was individual because every subject had a different cost, so everyone got a different transfer. So these caused the subjects to reduce dramatically their consumption of water, or the request for water. And we saw the same thing in the field. This is a statistically significant. You see how it goes up and down, just like in the predicted extraction path. So under status quo, it's consistently higher. Under decoupling, it goes up and high, but this difference here is statistically significant. And you can see how this trend follows very close our predicted trend, which was a decline, or it goes deeper, and then it stabilizes in a sort of like a harmonic way for the state variable. Now, those graphs are illustrated, but we also wanted to quantify the treatment effect. And we decided to calculate, or to use difference and difference as our method of calculating the treatment effect. And I am here showing you the difference in treatments. This is in the laboratory, and that is in the field. So for the laboratory, we have that on average, the individual requests for water went down 0.7 units once the treatment was implemented. In the field, the difference is 1.5 units of water per individual once the treatment is it's implemented. Or this is reduction. No, yeah, reduction. We have that in the laboratory. The reduction treatment had an effect of 1.5 units per period per individual once the reduction is implemented, and in the field it's 0.9 units per per period per individual once the treatment is in effect. As I mentioned before, when we compare the means and we conduct the statistical tests, the difference is not statistically significant, although here the treatment effect shows us statistically significant. Now for decoupling, in the field, in the laboratory, we saw that the effect was very dramatic. It had like a lot of effect. It's 2 units of water per individual per period of reduction. So once we apply decoupling, it reduces that much. And it's 1.2 units in the field. Now, how does that look in a comparison? These 2 treatments, elimination and reduction, you can see that it's almost like the laboratory in the field flipped sizes. So for elimination in the field, it was minus 1.5. That was the same for reduction in the laboratory. For the elimination in the laboratory was 0.7, it was 0.9 in the field. What is it explained by? As I mentioned, we don't have personal information of the participants, neither in the laboratory nor in the field. However, we do know that farmers have more experience with this issue than students have. So the fact that we got closer estimates than those predicted in the theoretical model for the field could be explained by the fact that farmers are more experienced in this issue than students are. But all of the treatments have the expected sign, which is a negative sign. All of them have a reduction in the requests for water. Now, what are the conclusions? What do we get from this? I don't know how are we
Well, fine.
Okay.
No, it's so interesting that we can take a little bit more.
Okay. Well, there's an inherent advantage of using experimental economics versus policy experiments or policy experimentation. What do I mean by this? We took a very complex problem, we simplified it, took it to the lab and tested with subjects here in the university and farmers in Mexico. What would be the alternative? Well, the alternative would be to design a policy and implement it in the real world. And after some years, we will probably have some results that may or may not be the ones that we are expecting. So there's an advantage in cost effectiveness, in the political costs of testing this versus doing it in the real world. There's a need to change how we see and how we give subsidies for pumping in the world, not only electricity subsidies, but diesel subsidies in India and in Pakistan, and some other different subsidies like the ones in Spain and whatnot. Farmers need to have the right signals and the right incentives for drafting an efficient amount of water and making their decisions more efficient as in crop and technology choices. And this is not a silver bullet. This is not the policy that is going to save the world. We need complementary policies to this subsidy, like conditional transfers. We need programs that incentivize the irrigation technology, programs that educate farmers in crop choices and whatnot. What are the policy implications of our research? Well, we saw that all the results have the expected sign. We expected them to be negative, all of them. There were differences between the laboratory and the field experiments. The difference could be significant, but at least in the decoupling treatment, we saw that the treatment effect and the trend was coherent with each other. Now, how do we choose between eliminating and decoupling the subsidy? Well, I wrote some pros and cons. So elimination is fiscally less costly to implement because we basically just eliminate the subsidy. We don't give it anymore. We save that money, and fiscally it makes more sense. Decoupling avoids the conflict of eliminating the subsidy, the political conflict and the political cost of doing it. And both achieve similar results in the field. We saw it in the laboratory, it was not clear, but at least in the field, both achieve similar results. So,
question.
Yes.
You think that elimination is feasible politically?
I don't think it's feasible. As I mentioned, the farmers are overrepresented politically in Mexico, not only in the Congress, in the national level, but also in the local level. So every time you talk about touching the subsidy, it's very, very costly politically. So I don't think elimination will be feasible for.
But is it the case that the decoupling is more expensive?
It is more expensive, but it's easier to sell to the farmers as a change in the subsidy. Like giving them a cash transfer, is easier to sell than to tell them we're not going to give you money anymore because the aquifer is being overdrafted. So politically, it makes more sense. Fiscally, it's more expensive.
So here we have the classic question of the social cost of a reform. And there are two aspects. One is the fiscal aspect, and one is let's call it the environmental aspect that has also fiscal consequences. So society has to make a decision, and luckily it's not us, it's the politicians, about what is better. And I think that, personally, I think, and also professionally, that the subsidy that will be administered in such a way that will minimize the environmental cost or the social cost is preferred. But again, it's always a question of trade-offs.
Yes, and that's one of the things that we take into consideration when we do the policy recommendations. We don't want to dream and tell the politicians, oh, you should eliminate the subsidy and implement the cost for water, because we know that it's not feasible. So our job, as I see it, is to come up with solutions that are feasible to implement in the real world, and we can compare them to other solutions and to measure what's the cost of each one of them and what will be the loss in welfare and whatnot for implementing different policies. So we found differences between the behavior of subjects in the lab and in the field. So, as I said, we do not have information on the subjects as of their education, income level, race attitudes, and whatnot, to calculate that or quantify those differences and come up with a number. But we do know that farmers have more experience. So the differences come from the fact that farmers have more experience in these issues than students that could be just naive and not even understand what the game is about. As I mentioned, we need to rethink the farming subsidies around the world. There's not only irrigation subsidies, but pesticides, fertilizers, and whatnot. Now, where does this take us to? What are the next steps? As I mentioned, this is a very, very simplification of a very simple exposition of the problem. But in the future, we could include, as Professor Rappaport mentioned, we could include heterogeneous farmers that account for the land size or for their irrigation technology or the crops that they do. We can include asymmetrical information on the aquifer or the type of land or the quality of the water. We can also include a stochastic recharge, because we know, especially with climate change, that we cannot account for the same level of recharge to the aquifer each year. So the recharge rates are stochastic. Also for technology choice and crop choice, so we could check the behavioral changes when we give the subjects the ability to change crops or change technology for irrigation and other changes. And these models could also be adapted to cases like California, India, China, Pakistan, Spain. So those are the things that we left pending with this research, but we are looking at them in the future. So thank you.
So we can open now the floor for questions from the guests also. There are any questions? Encarna?
I think
Any question? You usually ask questions.
Oh, yeah, Edgar, I was just curious. I mean, I don't know anything about human experimentation, but so these illiterate farmers, is there a reason they couldn't have been bred to? Was that just not like, was there not enough? Were there so many of them, or was there any way to accommodate that?
Well, the problem is that the game was in the computer, so they needed to know how to read the tables that we had in there, and that was the main barrier for.
So it was just practical to have some.
It was practical, yeah.
I mean, yeah. Oh, okay.
Yeah.
And do you have any like? Was it like a lot of people? Was it like
It was
half of them, or?
it was like 16 farmers total that we had to turn away.
Oh, so not very many compared to the total amount.
Yeah.
Oh, okay.
Yes.
So when I go to Sprouts, I notice that there's a lot of produce from Mexico. Has the import of produce from Mexico increased because of this subsidy?
I think there's many factors. One is the agricultural chapter of NAFTA came into play in 2004. So that definitely helps because there's less tariffs for Mexican imports. And then this is not the only subsidy that farmers have. There's many other subsidies that they have. So it's a combination of many factors that play with that. Yes.
Wait, any more questions?
Yeah, thank you. Did you look for any free riding within groups?
I haven't looked, but that's very interesting because when I didn't present it, but I saw it when I was producing the graphs and when I was cleaning the data. It's very evident when someone is free riding the efforts of conservation of others. And another
Almost following, on the output.
Yeah, because there's some subjects that always will request 10, no matter what, like 10 consistently. And some others you will see that the water table goes down and they kind of like reduce their request for the next period. If it goes up again, then they kind of like request for more water. So it's very easy to see that within groups. Another thing, curious thing.
Because you may wish to compare the degree of free riding between the lab and the field study. That will be very interesting.
That'll be, I think that'll be great for comparing. One curious thing that I found in the subjects were given scratch paper to make annotations or do whatever they want while they are in the experiment, and we collect that at the end. And in many cases, we saw many of the students trying to figure out how much the others were requesting. Like they will make like calculations and tables and see, and it was very, very fascinating to read the scratch paper after. And some of them will make annotations like there's no need to preserve water or what is the incentive. And it's like very, very interesting. I have those that paper if you want to check it out. It's really, really interesting.
You can put it in an appendix.
I probably will. It was very, very nice to see that subjects were like trying to figure it out, and that made me think that they understood the game at least.
At least they were involved.
Yeah.
So I have a question, two questions. One is more technical, and maybe Arnon can also answer. So what we can understand or see from the experiment is that even without knowing the background of the farmers or the participants in general, Some are more, or they have, let's call it an attitude or so, to adhere to a social norm of preserving the aquifer. Others are less, and their only objective might be only to increase their profits. Is there a way in a future experiment to try to assign some utility to some parts, or even randomly, to different types of behavior that will be different between the subjects?
I think it will be very, very difficult. Because basically you're asking whether you can measure greed and how you can measure greed. The typical way of doing it is with questionnaires, but I don't trust them at all. Because people will not admit to be greedy. So I'm not sure exactly how you can do it, how you can really go about it.
So now is the more challenging question. So Edgar, one of your objectives, implicit at least objectives, is to save society the political cost and arrive at a recommendation, or at least in the beginning of a policy recommendation at a much shorter period and much less cost. Yes. So now the next stage is to convince the government of Mexico or any other government how you are going to sell the results and the ideas that you spend so much time on to the government of Mexico, to the Comisión Nacional del Agua, that this is the way to go, rather than to apply a policy and then realize that it was a waste of time and damaging, or to do the huge experiments that were done, with a huge number of farmers that did not also succeed. Mm-hmm. So, what is your strategy in trying now to sell the idea?
Well,
because there are, as you said, so many other cases like Pakistan, California, Spain, that it can be a good selling point.
Yes. In the paper by Carlos Muñoz, he conducted a political study, to sort of say, on the viability of these, particularly decoupling, and how to implement it in Congress. Like he had like these very nice graphs of the left parties and right parties and how they would play off. And, there's some information in there. I know it's a difficult sell, especially because elections are coming, and elections are in 2018, so it's a difficult sell for now. But I think it is easier to sell from the environmental perspective than from the agricultural perspective. So there's a push in Mexico for policies that will sort of help adapt to climate change and sort of like avoid the consequence of climate change. You could go into them, although this is not very climate change related, as I mentioned, but the country is becoming drier and drier. So that is a selling point, and the government is willing to go very far in their policies to adapt for the climate change. So I think that's one of the ways to sell it. The other way would be to sell it just to individual states or governments. I know the state of Guanajuato, particularly the city of León, they have a very strong water agency, which is Zapal, and their presence in the city is very, very strong, and their policies towards water are very innovative. So if you can sell it to a smaller sample or a smaller piece of the government in Mexico, and it succeeds, it's probably easier to sell for a national level. So that would be a good strategy, I think.
warn you not to become a politician. Because that may take a very long time. And I think the second strategy that you described, convince a small group and let them push it, because they know more about politics than you do.
Yeah.
And nobody's asking them to write papers in order to get promotion. So I think it would be a better strategy to go to some key figures.
Okay. Luca, you have any questions?
Yeah, I was wondering about, you talk about laboratory experiment and field experiments, but both of these experiments are actually done in the laboratory, right? I mean,
Yeah.
only the subjects are different.
Yes. That's a distinction that is made in the literature. So basically when you use people that confront the problem in the real life, it's called the field experiments. Even though they're not done in the field, that's what it's called, field experiments. Usually, and it's not always the case, but usually when you use students, that's what it's called, a laboratory experiment.
Another question. You assume in your cost function and benefit function
Mhm.
that both are linear, right?
They both are linear. The benefit function for the first paper, the theoretical paper, it has a quadratic in there. But the one for the experiments, both are linear. Yeah, and that is also to keep things more simple.
But in the real life, would you expect that they would be different?
Oh,
Especially
definitely.
in the
Yeah.
paper?
Oh, yeah, definitely.
Because they would start switching to different crops, right?
Yeah, definitely. It's not linear, and it's also not just one function, because it depends on the crop choice, technology choice, the weather, and many other things. So yeah, in real life, a real benefit and cost function would be very, very complicated, much more complicated.
Then you run the risk of the subjects being confused.
Yeah.
And,
Was any of those strategies sustainable in terms of the aquifer? Because I saw values like going from 500 meters to 300 meters, minus 200 meters.
Oh yeah, well, in the first paper, how we measure is in respect to sea level. So that's why Kern County, some of the results go beyond or below sea level. So that's the negative numbers in there. In the laboratory experiments, we saw we use the height of the water table, which is with respect to the ground level. So that's why, and the bottom of the aquifer was 250 meters, which is, there's deeper wells in León. Some of them go like beyond 500 meters, but we decided just 250 just to keep it simple. But
do you have information? Was the drop like historical drop in this water tables?
as in, I didn't get the question. So information in what?
Like historical drop at the water tables.
Oh yeah, there's information.
But is it in hundreds meters?
That's
Yeah.
very, very well documented, especially in Mexico, because they run into catastrophe.
Yeah.
So inclusion of saline water from adjacent oceans.
Yeah. In the case of the aquifer of León, they conduct these type of studies periodically. But as I said, Guanajuato is an example of water management in Mexico. Some other parts of the country, they make these studies like every 10 years, it's not periodically. So it's more difficult to see, but in the case of León, it's easier because they do it very often.
But is it going into hundreds of meters?
Yeah.
Yeah.
And there's some wells in the city, well, in the outskirts of the city of León that go like to 500 meters and beyond. So, yeah.
And does the state of Mexico, is it involved in any desalinization process?
For groundwater?
Yeah.
That I don't know because
No, for drinking, and then it will affect groundwater.
there's a small desalinization plant in Baja. They are exploring that possibility, but no, it's not a mainstream thing. It's not, because it's very expensive. So
It's really not that expensive.
Yeah.
Getting cheaper.
Probably at one point in time they will start, as many other that happen. All right. Thank you for being here. You know, take a little bit more food on your way out if you want.
Thank you. That'd be great.
So Edgar, disconnect the cable so that the family cannot hear what we are talking about.
Oh yeah. No, I'm gonna take the computer with me.